Okay, I think we'll start. We'll give them 5 minutes. So we started a new topic yesterday, the last time, which was analog multipliers. Of course, in your telecoms, those of you who are doing telecoms, you are just representing a multiplier. And a cycle. So you got a signal XY, and we notice XY. You're using a small symbol cycle for an analog multiplier. But in this class, we are going to see how we design real analog multipliers. We said the symbol that we normally give is this one here. It's like a square with a triangle on top. And it's normally marked small x, small y, where we put the signal Vx to one input, signal Vy to the other input, and the output V0. Now, all these signals are with respect to the Earth. They're all referenced with respect to the Earth. So this signal Vx so those signals are at reference with respect to the Earth. So in the introduction, we did all this. You find an ID multiplier. Then we saw the limitations of our practical multiplier. And then went to how we practically realize or practically implement analog multipliers. So the first scheme was called the log anti-log. So we are going to be using log amplifiers, which you studied, and anti-log amplifiers, which you studied. And for log anti-log, we use this equation over here, that xy is equal to anti-log of log x plus log y. So to realize this circuit, if you look at this equation, you need two log amplifiers, which are these two over here, then an anti-log amplifier here, so that the result would be xy. But having studied the good log amplifiers and the good anti-log amplifiers, we see that they're very complicated. They have so many op-amps inside them. And then op-amps tend to suffer from offsets. So you have to put null offsetting circuits in each of the op-amps. And then further, the log and anti-log circuits we studied were unipolar. To make a log amplifier which is not unidirectional will be much more complicated, but it's easy to do so. But to make this circuit very complicated. So we don't use this circuit. We don't use this form of implementation. Or the form of implementation called the log anti-log. So all this we discussed in the previous class. Now the next implementation was the quarter square technique, or the quarter square scheme of implementation. So that is what you're going to look at today. If we get time, we'll also introduce the transconductance method, or sometimes it's called the variable transconductance method of implementation. So the resultant multiplier is called a variable transconductance multiplier. So this is the third scheme, and this is actually the most common scheme that we use. So let's go to the quarter square method. So in quarter square method or quarter square scheme, we make use of this identity that 1/4 into x plus y squared minus x minus y squared is equal to xy. If you want to do the maths, x plus y squared is x squared plus 2xy plus y squared. And if you expand the second term over here, x minus y squared will be x squared minus 2xy plus y squared. So if you subtract the two, you'll get 4xy, and a quarter of that will be xy. Now looking at this equation over here, to implement it, you did adders for x plus y, you need subtractors for x minus y, and then you need squarers. We need squarers, and then finally, we need to subtract again what we have squared, and then multiply the result by a quarter. So in block diagram representation, it looks something like this. So this is the circuit to be implemented. So if you have maybe here x, and you got y, x, you got y. So the output here will be x plus y. Here it will be x minus y. And here, use a squarer, x plus y all squared, x minus y all squared. And here, you're going to get x plus y squared minus x minus y squared. And then at the output here, you're going to get 1/4 x minus y, x plus y squared minus x minus y squared. And this will be just equal to xy. Now the circuit that enables us to do what is shown in the block diagram over here is this circuit over here. So in the notes that I've given you, I've not put whatever I've written here in red. Okay, I'll just show you how I get what I've written here in red. I just put the before times just to speed up things. So if you look at, let's call this amplifiers, let's call this one A1, A2, A3 to be my output amplifier. So our signal Vx is the same as our variable x. Our signal Vy is the same as our variable Vy. So I'll just be using, instead of having so many Sanskrits, instead of Vx, I'll just be using x. Instead of Vy, I'll just be using variable y. V there stands for voltage. Okay, so x will also stand for voltage. So if we start at the input of A1, the signal x comes in to the inverting input, and therefore the output of A1 is minus x. because an inverting amplifier for the signal X. Now, similarly, if you go to the bottom amplifier, A2, a signal Y. Okay, let's go back to input of A1. So a signal X is inverted, it gets out of the output of A1 as minus X. And then also at the input of A1, if you follow this bottom path over here, follow this bottom part, it comes over here. So you got a signal X over here to this through 5K to diode D2 over here. Now let's go to the bottom amplifier, A2. So a signal Y goes through the 10K, or you can just call it R. Set the same as the top amplifier. And then the feedback resistance is R for A2, so the output is minus Y. Okay, so that there's no confusion, let's just use this to be R. So they're identical to the top one. So the output of A2 is minus Y. Similarly, the input Y goes through this top path over here, and then is divided into two at this point. The top part goes to this 5K before going to D2, so there's a similar Y here. And the bottom part goes to this 5K, then goes to D3, diode D3 over here. So that's how we get these signals starting from the top of the resistors. The 5Ks at the top is minus X, minus Y. Then we go to X, we go to Y, then we go to minus X here, then we go to Y, and then we go to minus Y, then we go to X at the bottom, feeding D4. So I hope that is understood. Now to make the analysis simple, we'll simplify this diagram, starting at the outputs of the op-amps A1 and A2. So I've said consider a simplified circuit. So these are the four diodes. So the diodes D1, D2, D3, D4. So the top diodes D1, D2, current will flow from left to right. The bottom diodes D3, D4, current can only flow from right to left. So for D1, if you look at this circuit, it's got signals minus X minus Y. And for D2, we have X and Y. So I'll just put those signals here. So for D1, I've simplified it. Instead of writing minus X minus Y, I've written minus into brackets X plus Y. So this will be minus X minus Y. And the signal to D2 is just X plus Y. And the signal to D3, if we just look at the circuit again, here is our D3. So the top signal is minus X. The bottom signal is Y. So it's minus X plus Y for D3. will rearrange it in a better form. And then the bottom signal is minus y plus x. So here it is for D3, minus x plus y. The signal to D4 is x minus y. Now, for D3 and D4, I can write minus x plus y as what I've shown over here. I can put in this format, minus into brackets, x minus y. If you expand this, will be minus x plus y. And the bottom one will just remain signal to D4, just remain x minus y, just as shown over here. Okay, so now let's start the analysis. So let's consider the circuit comprising of D1 and D2. Now this circuit is, this diodes are actually going to be performing the squaring, as we shall see. That's why I've said consider the squarer comprising of D1 and D2. Consider the squarer comprising of D1 and D2. Of course, as to now yet, I've not proved that the square. But let's continue. So if you just consider diode D1 and D2, the input to the diode D1 is minus into bracket x plus y. Input to diode D2 is x plus y. It's the voltage x plus y. And let the individual currents from the top diode, I'll call it IA. And the bottom current from diode D2, I'll call it IB. And the resultant current going to the ground is actually a virtual ground. I'll call it I1. Now that is from this circuit. This is what we have over here. This point here is earth. This point is virtual earth. So this virtual earth extends up to this point. And to make life easy, let x plus y be equal to a new variable z. So let x plus y be a new variable z. So it means for the top diodes, this signal over here, I can call it as minus z. And for this signal here, I'll be calling it z. So the signal to D1, which is minus x plus y, minus into bracket x plus y is the same as minus z, because I'm saying let x plus y equal to z. And the signal going to the bottom diode D2 is just x plus y, so it will be equal to z. Now we know that for a general diode, ID is I naught e to the V forward of the diode over an eta Vt minus 1. So we'll start with the easy one, which is D2. So we want to find out what is this IB for D2, this current over here. So we can write IB, which is the forward current for diode D2, is I naught e to the Z from equation 1. It was supposed to be the forward bias voltage, but the forward voltage is actually x plus y, which is the same as z. So it should be e to the z divided by eta Vt minus 1. And to make life easy, I'll introduce a new variable. k, where k is equal to 1 over eta vt. Now, there's a typing mistake here. K where k is equal to 1 over eta vt. So from equation 3, I can write that IB is I naught e to the kz minus 1. Now, using Euler's relations, we know that e to the power x can be written as 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. So we can write e to the kz in this equation 3 over here, this first term. If I take I naught to be common, can be written as 1 plus kz instead of x plus kz squared over 2 factorial plus kz cubed over 3 factorial, etc., etc., all minus 1. And we get equation 4. Now, these higher terms after the third factorial are very small, so we can neglect them. We can neglect any higher term starting from 3 factorial. And the 1 in the beginning over here will cancel with this other 1 over here. So I'll just remain with the 2 times kz plus kz all squared over 2 factorial, which is just 2. So we can say that IB is I naught into kz plus kz squared over 2 factorial, which is just 2. So that's how we get 5. Now we can do the same for IA. Now I've just given you the result. IA, okay, maybe some of us are not in the same page. I can repeat the same for how to determine IA. IA is the current that passes through the first diode. This current over here. Now V forward for this first diode over here is minus Z. So if I substitute it in equation 1, here, then instead of I diode, I'll just write it for the second part over here. So it will be IA is equal to I naught into bracket E2 instead of V forward, just minus Z all over eta Vt minus 1. And then I can apply Euler's relations. I naught into 1. First of all, I have to substitute. Let me do it in 2 steps. This will be E to the K minus KZ minus 1. Because K is 1 over eta Vt. And that's when I apply now Euler's relation. And I get I naught into 1 plus minus kz squared over 2 factorial, etc., etc., minus 1. And then you can come over here and you get IA is I naught. The ones will cancel. I've missed one term, sorry. Let me just come here. So this is I naught into bracket 1 plus minus kz plus minus kz squared over 2 factorial plus dash 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 plus 1. So the 1s will cancel, and I'll remain with I naught into bracket minus kz plus minus kz squared divided by 2 factorial. So this minus squared is just positive. 2 factorial is just 2. So this is your IA. So I've done for those who are not able to see directly, because I've just put the result here in the notes instead of typing it twice. So we got IB is equation 5. And I said similarly, A is that. Oh, I mean, I did it. Okay. So you get this minus kz equation 7. Is this equation over here? Minus kz plus minus kz squared over 2 factorial. And therefore, current I1, which is the sum of the currents, this is current I1 over here. IA is the current of the first diode. IB is the current of the second diode. Therefore, I1 is just IA plus IB. So if we sum these currents, we could leave it there. So if we sum these currents, I1 is IA plus IB. IA is equation 7 here, which is what we just derived here. IB, we had earlier derived it, is kz plus kz squared over 2 factorial. That's equation 5. So if you add equation 5 to equation 7, the kz here in 5 will cancel with the minus kz of 7. I naught is common, so it'll just remain with 2 times kz squared divided by 2, because in equation 7 the minus kz squared, if you square it, it becomes positive. So that's how you get equation 8. So I1 is IA plus IB, which is just I naught into 2 times kz squared over 2 factorial. The 2 factorial is just 2, so this 2 will cancel with the other 2 over here, so just remain with I1 is just I naught kz squared. So that's how we determine the sum of the currents flowing through diodes 1 and diodes 2. Next, let's consider currents flowing through diode. So if you look at this equation 9, you can see there's a square function. It's squaring the current is some scalar, k squared, into z. Z is the summation of the 2 voltages, x plus y. So that's why you say this is a squaring. Those diodes are performing a squaring function. Okay, so next let's consider a square rack comprising of diodes D3 and D4. Now diodes D3 are these ones. This circuit, in the first circuit over here, diodes D3 is here, diodes D4 is here. Now diodes D3 is being fed by a signal minus x plus y. Diode D4 is being fed with a signal x minus y. And I told you I just drawn it here again. We can rearrange the current, the voltage across the diode D3 as minus into bracket x minus y. so that the terms in the brackets are common. So the bottom diode, D4, is just simply x minus y. And then I will use a new variable. I think I've used P, so I don't know, we'll check in the notes. So this x minus y, I think I've used a new variable P is equal to x minus y. So it will make our analysis easier. So let's go to the notes and see. Yeah, I've used the variable P. So P is x minus y. So the voltage going to the D3 is actually minus P. And the voltage going to the second diode, sorry, D4, is x minus y, which is P. Because I've used the substitution here, I've said let P be equal to x minus y. Therefore, we can say for, and let the current through diode D3, I'll call it IC, and the current through diode D4, I'll call it ID. I'll call it ID. So in diode D3 and D4, the current can only flow from the right-hand side to the left-hand side. And the sum of these currents, I'm calling them I2. And this point is the virtual add. So let's go through using the notes. So I've said let P be x minus y. Therefore, for a diode, for ID is the bottom diode here. The bottom diode, I'm calling it the current there through ID. So ID will be equal to I naught e to the V forward divided by neta Vt minus 1, but the forward voltage now is P. So we can say that ID is I naught e to the P divided by neta Vt minus 1. And then I'll simplify it by using a variable K, where K is 1 over neta Vt again. We had used it earlier. You can see. So we can write that ID is I naught e to the Kp minus 1. And if you use Euler's relation of e to the x is 1 plus x squared over 2 factorial, etc., you'll get ID is I naught 1 plus, instead of x, it's Kp plus Kp squared over 2 factorial plus Kp cubed over 3 factorial, etc., all minus 1. The ending one will cancel the beginning one, and the terms greater than 3 will be small that we can ignore. So we just remain with the second term and third term. And so next we go to find IC. So now we can just state it. No need to go through the basic steps again. So similarly, IC is just I naught instead of Kp in this equation here. We just put minus Kp plus minus Kp all squared divided by 2 factorial. So I think there's a typing error here also. Let's remove this. So we found out what we wanted. We found out IC, and we found out ID. In this, let's just call them arbitrary numbers. Let's assume this is question 10, and this is question 11. So we found out IC, and we found out ID. Now let's go back to the diagram. It is just here. So IC is this current over here. ID is this current over here. So the sum of currents going away from the junction should equal to the sum of currents moving away from the junction. So the unknown is I2. So if we apply KCL at the node, we'll get IC plus ID is equal to I2. I think what I deleted was I was supposed to have written it was supposed to be I2 is equal to IC plus ID. That's what I deleted, I think. But I think I saw that it was just written equals. That's why I deleted it. It didn't make sense. So here, after this, if you apply KCL, we get that IC plus ID is equal to I2. And therefore, if we add IC to ID, we get this equation here, which is 12. If you add these two equations, IC plus ID is equal to I2. And if you add those two equations, this Kp will cancel this Kp if you add them. And these two terms, the Kp squared and the minus Kp squared, this becomes all positive because square of a negative number is positive. So you'll get I2 as equal to 12. For those of you who don't understand, maybe I can just do it. It's just very simple. So let's just use IC plus ID is equal to I2. And the IC is actually 11. This is I0 minus Kp plus Kp. I'll just use the term, use positive now. Okay, maybe some people might be lost. So let me just go in steps. So minus Kp over 2 all squared plus ID. ID is equation 10. ID is I naught into brackets Kp plus Kp squared all over 2. So if you take I naught to be common, this Kp will cancel this Kp. And in the first square bracket, minus Kp squared is just the same as positive Kp squared. So you get this positive Kp squared here and another positive Kp squared over here. So you get, if you add them, you get twice Kp squared. So just remain with 2 Kp squared. Over 2 factorial. Because the Kp squared divided by 2. Kp squared divided by 2. So the 2's will cancel. So it will just remain with I naught into Kp all squared. So this is how I get this. This is how I get this equation 12. So 12 and that's how we get equation 12. So I2 is just I naught into Kp squared. It is just the summation of the currents IC and the currents ID is your I2. So I've drawn a reference circuit over here. We look at this figure. Let's call this one figure A, compressing the op amps. So I've shown the currents I1, I've shown the currents I2, and I've also shown a current I3. I1 flows from the left to the right because the diodes are forward biased in that direction. I2 flows in the opposite direction from right to left because the diodes, the bottom diodes are biased in the opposite direction. Now, since in figure A, this is the op amp A3, the last output op amp. So if we assume an arbitrary current I3 flowing in that direction, then if you apply KCL, currents going towards the node is equal to currents going away from the node. I've gotten this equation here. I1 is current going towards the node. I2 and I3 are currents moving away from the node. So if you apply KCL at this node over here, and we solve for I3, we'll get I1 minus I2 is equal to I3. So that's how I get this equation. Let's call this equation 12. Let's call this equation 13. So in equation 13, I've written in the type notes, I3 minus I3 is equal to I1 minus I2, which is what we've gotten over here just by applying KCL to the node. This is what we've gotten over here. So all we have to do is to substitute the values of I1 and I2. And we've derived I1 and I2. I2 is here. I2 is equation 12 over here. Equation 12 over here. And I1, let's look for I1. I2, where is our I1? Should be here somewhere. Wait, I1 was this is I2. What do you mean then? Okay, I1 is equation 8, equation 9. I1 is IA plus IB, which is I0 into KZ squared. So this was I1. And now we've gotten I2 from 12 over here. And therefore I3 is I1 minus I2. So it's I0 KZ squared minus I0 KP squared. So we can get the common terms outside. I0 is common. So we can write it as I0 into KZ squared minus KP squared. And then we can get the output of A3. Output of A3 if we look at figure 1 over here, let me rub some of this so that it looks a bit clear. So V0 is with respect to the ground. So the minus input of A3 is ground. Sorry, the positive input of A3 is ground. The minus input is vertical ground. So the drop across the feedback resistance, the positive side is pointing towards the ground. The negative side is pointing towards the positive of our V0. And we can write that I3, the drop across RF is I3 into RF. Minus of it is equal to V0. Because a drop across the resistance RF, the positive side is here, is on the left-hand side. And that positive side is connected to the earth, or to the virtual earth. And the opposite side of the resistance RF is minus. That minus side is connected to the positive of the V0. So that's why I've written this equation here. If you go back to the type notes, let's call this one 14. So I can write as 14. V0 is minus I3 into RF. Then we substitute for I3. I3 we get from equation 13. I3 is I0 into brackets, into square brackets, KZ squared minus KP squared. So if you substitute that one, you are going to get, let's call this one 15. We'll get 15 if you substitute for I3. And therefore, if we square inside the square brackets of 15, inside the square brackets, the first term will be K squared, Z squared, minus K squared, P squared. So we'll get the squared K squared term out of the square brackets. So we are going to get 16 And then now we resubstitute the variables that we put in for Z and P. Now Z was X plus Y, and P was X minus Y. So we'll get V naught as shown, I'll call it 17. We get V naught as shown in equation 17. So that is our output equation. V naught is minus RF I naught K squared into the square brackets X plus Y squared minus X minus Y squared, close the square brackets. Now we got to compare this, the expression on the right, to the expression of the identity. So I've said for this circuit to multiply, it must mean that this term minus, the minus sign just means that the voltage been inverted. Okay, the minus sign just means that the voltage been inverted. You can put another inverter at the output to make it positive. So it must mean that RF I naught K squared should be equal to a quarter. So we substitute RF and use the equation. Let's call this one equation 18. So I'll use RF I naught K squared should equal to a quarter, or we can solve for RF as equal to 1/4 I naught into K squared. But you got to remember that K, the substitution we used, K is 1 over neta Vt, and neta is equal to 1 for germanium, neta is equal to 2 for silicon, and Vt is Kt over Q, which is about 26 millivolts at room temperature. So it means that this circuit can multiply so long as we satisfy equation 18, where RF, we design it so that it's equal to 1 over 1/4, 1 divided by 4 I naught K squared. So if you want details of K, neta is 1 for GE, 2 for S. Now we can come to the conclusion and say that since squaring is performed by using diodes, which is very approximate, because remember we're using these Euler's relations, ignoring some terms. So I've said since squaring is performed using diodes, which are very approximate, the above realization results in multipliers which are fairly inaccurate. And thus this implementation is rarely used. So this scheme over here, and in fact I could have added some more over there, you can see how many op-amps are used over there. And all the op-amps are going to be suffering from offsets. You have to have null offsetting circuits for all the op-amps. So it's going to be a tedious way to try and multiply two analog signals. So this implementation is just academic because we're trying to use the identity, but practically it's impossible to design a good multiplier with high accuracy using this scheme. Now the next scheme for implementation of multiplier, analog multipliers, is called the variable transconductance method. This is called the variable transconductance method. It's called that way because you're going to vary the transconductance of an amplifier with another signal. So as an introduction, I've said in this scheme, the transconductance of a differential amplifier is varied by a second signal to effect multiplication. Now, the simplest implementation of this scheme is called the basic two-quadrant multiplier. So this is a multiplier whereby maybe you can get plus minus x into y. The result is only going to be available on two quadrants. This is a symbol. So one variable can only take a positive value, the other can take both positive and negative. So from your early maths, normally we have four quadrants. I don't want to waste time going into there. So if this is, say, your x, and y is only positive. Sorry. As you can get positive x, so there's 0, but y is only positive. So you get results in this quadrant and this quadrant. So let's see how it's implemented. Now for this multiplier, we're going to be using a differential amplifier, and for a general differential amplifier, we can write that V naught can be written as, V naught can be given as minus GM into V1 RL. Well, RL is the load resistance, V1 is the input. Now, if the GM can be varied by another signal V2, so we can write that GM is, say, some scalar into V2. So we can substitute for GM in equation 1 by KV2. Then we get this equation over here. We just substituted. Why is this thing so big? So we can write, this was supposed to be our GM, V2, to some scalar. Let's go back to the beginning. So in equation 1, if GM is varied by a second signal, so we can write GM is equal to some K into V2. So if I substitute, maybe this, let's call this one equation 2. And let's substitute this GM over here. Then we'll get this equation 3. We'll get this equation 3 here. So we'll get V naught is some K2, V1 into V2, where K2 takes into account the first scalar into RL. So that's a multiplication function. Now let's see a circuit which can implement that. So this is one such circuit, this figure 1. And I'm sure you people have used this in the labs. So this is your general differential amplifier. The current in the here, we normally call it IEE sometimes. So these are three-way power supply. Now, if you've been to the lab, this circuit is very difficult to get to measure the two inputs and the outputs and V2 with the same scope. Because the grounds are different. The ground of the signal V1 is different to the ground of the signal V2. They don't have the same reference. Signal V2 is connected to minus VEE. Okay, so let's continue. So for this circuit, if GM is the transconductance of Q1 and Q2, we can write that V0 is minus GM into V1 RL. But for this circuit, IEE let's start again. V0 is minus GM, where GM is the transconductance of the combination of Q1 and Q2. But GM can be written as IEE divided by VT. Now IEE for this circuit over here is given by V2 minus a drop VBE, because if you have to put VBE over here, or you can call it VBE2. So IEE is V2 minus VBE over RE, which is approximately V2 minus 0.6 if it's a silicon transistor over RE. So we can write GM as V2 minus 0.6 if I use, let's call this equation 1, let's call this equation 2, let's call this one 3, let's call that 4. So if I use equation 2 with IEE given as 3, then I get equation 4. So GM, how GM varies, is equal to V2 minus 0.6 all divided by VT into RE. And therefore V0, we use 1, equation 1, just minus GM, where GM is the whole of 4 into V1 into RL. Now this circuit is just there to illustrate how we multiply the two signals. So we vary IE with the voltage V2. But this circuit has got lots of problems. It's a very important circuit. We use it in telecoms a lot, but we don't use it in this way. We don't use it in this way. If you notice in this circuit, V2 can only be positive with respect to VEE. If you want to multiply DC voltages, or if you want to multiply to work all the way up to DC. So V2 must first overcome VBE2, which is approximately 0.6 volts. That's when the current will start flowing. The current is given by V2 minus VBE2 over there, all divided by RE. Now in the lab, I'm sure maybe you have used this circuit. but we don't use it this way. We use it to multiply AC circuits. Sorry, AC signals. Whereby we bias Q3 correctly, but put a capacitor in between. This is what I mean. Maybe in the labs, I don't know what multiplier circuit you're doing in the labs. Maybe somebody will tell me. I don't take you people for labs. So you can ground one side and put a signal V1 with respect to the ground and get an output here. And then for the second signal, you have to bias it correctly. Remember, this is minus VEE. So you need a three-way power supply. So you have to bias this one correctly. And then you have to use an isolation capacitor. And then you put a signal V2 respect to the ground. So this way, V1 can be DC or AC, but V2 must be AC. Could somebody tell me, those of you who are doing multipliers in 5th-year labs, can you tell me which circuit you're using? Is it this circuit? Anybody in 5th year? CR? Oh, Brian, you're saying you're using 4 quadrants. Okay, Brian, switch on your mic.
Yes, we're doing 4 quadrants.
Kimiti Brian. Kimiti Brian.
Yes.
I want to listen to your music. Why are you disturbing us, Kimiti?
That's not my music.
It's your music. It's coming from your computer. Somebody was saying you're doing 4 quadrant. So the circuit does not look like this. The person. Okay, we'll just continue. So this second circuit which I've drawn over here is essentially the same as that of figure A. Figure A, V2 can only be positive with respect to minus VEE. You can multiply DCs, but also there'll be a large error because the GM IEE there is V2 minus VBE over RE. But if you use this diagram I've drawn over here, let's call it figure B. For multiplications of AC, and this is a very good circuit, figure B. It will multiply both the positive and negative. The only limitation is that the signals V1 and signals V2 do not have a common reference. So all this implementation has got many disadvantages. The output also is floating. It doesn't have a common reference. We want an output with respect to the ground. We want the signal V1 with respect to the ground. We want the signal V2 to be applied with respect to the ground. Okay, so these are these circuits. So given the limitations over there, Number one, the output is floating. It doesn't have a common reference. Number two, also, signal V1 should be less than 4 VT. I think from your third year analog electronics, if you drew for differential amplifier, if this was the first transistor, you'll find here this voltage over here. This is the difference voltage at the input. This is about 4 VT, where the current transfers from one transistor to the other for the difference amplifier. Because the sum of the two currents should always be equal to, for the differential amplifier, the sum of the two currents, the magnitude should be always equal to AEE. I hope you saw those curves when you're studying different amplifiers. So number two there, signal V1. V1 is the input to the difference amplifier. It will always be less than 4 VT to avoid Q1 and Q2 operating as switches. Because once they saturate, the current can't pass anymore. Then also signal V1 and V2 do not have a common ground. That's what we mean. If this is, let's assume this is the representation of that multiplier, and this is our X, Y. So this is our signal V1. So V1 is actually connected towards the ground. But V2 is connected to minus VEE. And the output, V0, is floating. There's no connection. It's actually floating. It's not connected with respect to the ground. But the advantages of these circuits are as follows. It's got only 3 transistors, so it's very cheap. Number 2, it lends itself to IC fabrications. Number 3, it has got a very high frequency response. If you design it correctly, it can work up to the gigahertz range. And finally, I've concluded that because of the above advantages, this circuit tends to have widespread use or applications in small signal multiplication circuits, as those found in small signal processing circuits, in small signal processing circuits. You can say, let me put there, e.g. communication receivers, transceivers, transmitting circuits, for generation of DSB or double sideband signals, FM signals, AM signals, modulators. So modulators for both DSB, FM, AM, and also in the modulators, and also for phase modulation and also demodulation. So communication receivers are those very expensive receivers which are used by the military, the broadcasting stations, etc. Those are referred to as communication receivers. They're not the cheap domestic receivers we use in our houses. For example, to transmit maybe signals from the KBC studios, for example, next to the university, next to Newsstand, is it? Norfolk Hotel. There, to say other areas of Kenya. Of course, the first nearest point is Limuru, which is very high up. So they'll be using communication receivers and to transmit and also to receive, you need multiplier circuits. Multiplier circuits are also used for frequency translation. If you multiply two cosine waves, you get the sum and the difference of the two cosine waves. And they're also used for reception. You can be used for demodulation. So I'll just stop over there for now. There's a lot that can be said over here. Most of the modems that we use for both modulation and demodulation, they use multipliers, but not this one. This one we've shown. There'll be four quadrant multipliers, which will be our next topic. Okay, so let's see how we can improve on this very basic multiplier. No, so a simple circuit, a simple improvement is to use this circuit over here. So now the difference amplifier comprising of Q1 and Q2, the output goes to a difference amplifier. So now the output is with respect to the ground. So at least now the output is back to the ground. Now V1 can also be put with respect to the ground, but V2 is still not with respect to the ground. So this is just another implementation whereby if the current at the emitters of Q1 and Q2, you call it IEE. Now, I've not written it, although I've typed over here. I'm calling it IEE4. Why? I don't know why I did that. Q4. Okay, so if this is the current, now if you apply KVL, if you apply KVL to this part over here, it will be identical to applying KVL because these are matched transistors Q4 and Q3, matched over here. So you can use this VB4 or VB3. So if you start from minus VEE, climb up VBE, drop across RE. So let's find out the current through this resistance RE. So current through the resistance RE is just given by that. Current through the resistance given by that is V2 minus VBE4 or VBE3, doesn't matter, or VB3 all over RE. Now, if V2 greater than VBE4 or VB3, then we can write that IEE4 can be approximated to be V2 over RE. And therefore, V0, which I have not written over here, the total results. So we know that V0 is equal to minus GM 12 into RL, and V0 is minus GM. sorry, instead of GM, we can write it as IEE4 over VT into RL, or we can write that V naught is a minus IEE4 can be written as approximately V2. Oh, there's a V1 missing here. I'm getting tired of what. Let me do it again properly. So here I'm just getting this voltage here, V naught. So for the general difference amplifier, V naught is minus GM 1, 2. 1, 2 means Q1, Q2 into V1 into RL. But GM in this case is V2 over RE into VT into V1 into RL. So the output can be written as minus K V1, V2, where K takes into account all that. And that's just the output V naught at the differential amplifier. We studied the difference amplifier, so I won't waste my time on that one. Difference amplifier. We did it earlier on. I won't waste my time on that one. How to get from here to here. Okay. So this circuit over the earlier circuit, the only advantage is that the output now is with respect to the ground. That's an advantage. So the output and V1 is respect to the ground. The other signal V2 is still with respect to minus VEE. So this is still a two-quadrant multiplier if V2 is a DC. And it will give rise to large errors because the signal being multiplied is actually a V2 minus VB4 over RE. An improvement of all this multiplier is to use what is known as the Gilbert's multiplier cell. Gilbert is the scientist that came out with this configuration of how to connect two differential amplifiers in parallel at the output and vary their transconductance with another differential amplifier for the signal V2. So I've said this is an improvement on the basic differential multiplier and does away with most of the former's limitation, but retains the advantage. The advantage is the high frequency part. The disadvantage, the other advantage is now with the Gilbert multiplier, all the signals are with respect to the ground. We'll start with the simplified Gilbert multiplier with the floating output, but we know how to convert a floating output to be with respect to the ground by using a difference amplifier. So let's look at the circuit that performs the multiplication, which was invented by Gilbert, hence the name Gilbert's multiplier. So this is called the Gilbert's multiplier cell. This is the cell or the part of the circuit that performs the multiplication. So Q1 and Q2 forms a difference amplifier. Q3 and Q4 forms a difference amplifier. Their outputs are connected in parallel, but in a very special way. And then to vary the transconductance, we have the other difference amplifier comprising of Q5 and Q6. So this is how the circuit looks like, the Gilbert's multiplier cell. Of course, if you look at the circuit, the output is floating. It doesn't have a common, it's not with respect to a common ground, but we know how to convert that output to have a common ground. So let's analyze this circuit and show that it performs multiplication. Now for this circuit to work, Q1, Q2, Q3, Q4 must be matched transistors. The best way to get transistors matched is to fabricate them at the same time in one chip. And also Q5 and Q6 must be matched transistors. So let me ask you the question again. Is this the circuit that you're doing in the lab? Could somebody answer me? Switch on the mic. Kimiti Brian, what are you doing in electronics lab?
Yeah, we also did Gilbert cells.
You've already done it.
But we did not implement it in the lab.
What do you mean you did not? You simulated it using a computer program?
Yes.
Which program are you using for simulation?
It was Proteus.
And it worked?
Yes.
But why didn't you build it? What's so difficult with this? It's just a few transistors, 6 transistors, maybe 7.
I tried, but it wasn't bringing the desired outputs.
Why?
I'm not sure.
Maybe you can scan the circuit, give it to the CR. You can WhatsApp me so we can look at it in the next class.
Okay. Okay.
So this is the Gilbert's multiplier cell. This is the part of the multiplier that performs the actual multiplication. So we've got a constant current source at the bottom over here, which gives a current which I'm calling I total. I total will be the sum of the currents that pass through Q5 and Q6. And it's formed using a constant current source. I hope you know how to build constant current sources. You must have studied constant current sources maybe in your third year. And even as we did one when we were doing the log amplifier, that one was using an op-amp. You don't need to be that expensive. Okay. So let's see how this circuit works. Now there are some parts of this circuit, as I said, like for example, the constant current source, you can't see the complete circuit of it. Okay. So The assumptions we're going to make is that Q1, Q2, Q3, Q4 are matched transistors. Q5 and Q6 are also matched transistors. The base currents are almost zero because the HFEs are very large, so base currents are negligible. The betas of the transistors are very large. And then I'll assume that the circuit is already biased properly. We don't want to put those biasing resistors here. So that I'm not going to be considering the quiescent currents flowing. I'm only going to analyze it using the signal currents. So for example, supposing when all the input voltages are zero, maybe 2 milliamps was flowing through the collector of Q1 and 2 milliamps was flowing through the collector of Q4, say. I won't consider that current. I'll only consider the dynamic currents, which are due to the signals to be multiplied. So there'll be a shift from the quiescent point as a result of the voltages V1 and V2. So although I'll be using capital letters to denote the currents through the collectors of Q1, Q2, Q3, Q4, Q5, Q6, I'll be using capitals, but those capitals, capital letters, are for signal currents, not quiescent. Okay, so this circuit, you've got to know it. There are just two differential amplifiers in parallel here, another one at the bottom here. So this is what I've said in the analysis, that we assume Q1, Q2, Q3, Q4 are matched, and the betas of the transistors are much, much greater than 1, such that IC is much, much greater than IB, IE, IB, or the effects of IB can be neglected. So let's look at this. Let's look at this circuit again. So let's start from the top left. So you've got a transistor Q1. I'll be calling the current going through the collector of Q1, this current. I'll be calling it IC1. The current here, IC2. The current here, IC3. Current here, IC4. So these are signal currents. They're not quiescent. Signal currents ride on top of quiescent. Okay. Then the current at the collector of Q5, I'll be calling it IC5, collector 5. Current in this one, I'll be calling it IC6. Okay, so these are the dynamic currents. Which ride on top of the quiescent. So I said, for example, if IC1, when there's no signal, I'll say 2 milliamps, and I put a voltage V1, and it changes from 2 milliamps to 3 milliamps. So they change the delta from the quiescent, there will be 1 milliamp. So that's the current I'm considering. That's the current as a result of the input voltage, not the currents used to bias the system. And I'm using capital letters, even though they're signal currents. So please note that bring confusion. Okay, so let's start. So if you look at this diagram over here, the current, the signal current IC1 of the collector comes to the emitter. The signal current IC2 comes to the emitter. So IC1 and IC2 add up to form the collector current of this bottom transistor. Similarly, to consider Q3, Q4, And of course, the other thing we are assuming in the analysis is that the collector current is identical to the emitter current because the betas are very high. Of course, you know alpha is the ratio of IC to IE. IC, IE is beta plus 1 into IC. Sorry, beta plus 1 into IB. Oh, I'm confusing myself. IC is beta IB. IE is beta plus 1 into IB. Okay, but if the beta is very high, that addition of 1 is small. So we'll assume that all the collector current goes to the emitters of the respective transistors. So the emitter of Q3, I'll get IC3. At the emitter of Q4, I'll get a signal current IC4. And the summation of these two signals will form IC6. And then at the emitter of Q6, we get a current which is identical to IC6, and it will add with another current which is identical to IC5 to form the total current which you're calling IT. So these are the first equations we're going to start with. So I've written them here. So I've called it the dynamic current relations are, not the static or the quiescent, the dynamic, the signal currents, in other words. We have I1 plus I2 is I5. I1 is the same as IC1. So this is this one. IC1 is the same as your I1, IC2, I2. So this current plus this current appears at the emitters to this one. Similarly, I3 plus I4 is I6. So you get equation 2. I3 plus I4, I6. And then finally, at the emitter of Q5 and Q6, we get IC5. IC6 is equal to IT. So that's equation 3. So I hope that is understood. Now let's consider the voltage, input voltage current relations of a general differential amplifier. So this is a general differential amplifier. If the input voltage is V1 between the two inputs, we notice the output. Then for the general differential amplifier, we know we can write that V0 is minus GM12. The 1 means transistor 1, 2 means transistor 2, into V1 into RL. So GM12 is the transconductance of the differential amplifier comprising of transistor 1 and transistor 2. The minus sign there is because the signal is inverted. When the input goes high, transistor 1, the collector voltage falls, so it's inverted. Okay, now also in this circuit, if you look at this circuit over here, we can write V0 as a drop across RL to the left and as a drop across RL to the right. The current flowing through Q1, we'll call it I1. The current flowing through Q2, the collector current, call it Q2. So we can write V0 as follows. VCC minus I1 RL, that is the potential at the collector of the first transistor, minus VCC minus I2 RL, that's the drop across the second transistor. So if we subtract the two, we're going to get the voltage across the two transistors, the collectors of the two transistors. So if you open this bracket of 5, open the bracket of 5 and get VCC minus I1 RL minus VCC plus I2 RL. So the VCCs will cancel. So I'll remain with a positive R2, I2 R2, and negative I1 RL. So we can combine them and write them in the form of I2 minus I1 RL. That's equation 7. But I want to put it in the form of the first collector current of the first transistor minus collector current of the second transistor. So I want to put I1 first. So I have to put a minus sign. So we get V0 can be written as minus into brackets I1 minus I2 RL. So equation 8 is just the same as equation 7, but we need it in this form. So now we can equate equation 8 to our first equation, which is equation 4 over here. V0 was also equal to minus GM12 into V1 RL. So if you equate 4 and 8, so what I've done is I've written 4 on the right hand side of 9, and I've written 8 on the left hand side of 9. So I'll get minus into brackets I1 minus R2 into RL is equal to minus GM12 into V1 RL. So the minuses will go, and here I've just rearranged equation 9 and put the currents on the right hand side to get 10. But actually it's better if the I1, I2 was on the left hand side, because that's what we'll be using a lot. So for 10, I'll be using it in this form: I1 minus I2 is equal to GM12 into V1. That's the standard form I'll be using it in. So now let's apply this result 10 to the transistors Q1, Q2, Q3, Q4. Now, if you look at, I wish I could use a minimized version of this diagram. Let me just draw the general differential amplifier here next to this one. So we got this expression for this circuit I1 minus I2 equal to GM 12 into V1. Let's just check that it's correct. Yeah, I1 minus I2 is GM 12 just means transistor 1, transistor 2 into V1. So this gives us the relationship between the collector currents and the input voltage and the GMs of the two transistors. So I want to apply this equation to Q1 and Q2 to get 11. Q1 and Q2 to get 11. Now this is our Q1 in a Gilbert multiplier. This is a Q1, this is a Q2. Now if you look at this differential amplifier formed by Q1 and Q2, it's identical to this one, our general differential amplifier. Therefore, the collector current relationship will be minus I2 is GM 12 into the input voltage. But the input voltage V1 at the base of Q1 is positive and the base of Q2 is negative. All right. Now let's apply this again to transistor Q3 and Q4. So what will it be? For this equation over here to be applied, V1 now is actually going to the base of Q4. And the collector current is I4. And the negative is going to the base of Q3. So for that, we can write that I4 minus I3 will be equal to GM 34 into V1. So that's how we get equation 11 for the first Q1 and Q2 is identical to the basic differential amplifier. And for Q4, Q3 and Q4, we get I4 minus I3 is GM V1. So that's the voltage current relationship for the transistor Q3 and Q4. Now let's consider the output voltage of the cell. So the output voltage of the cell of the cell is V0 here. Now V0, these are positive, these are negative. Is the drop across this RL to the left minus the drop from VCC across RL to the right. Now the drop across RL to the left here, if we start at VCC, it will be VCC minus the current that goes through this collector IC1 plus the current that goes to the collector IC3, because these two currents come from RL to the left. Similarly, the drop across the RL to the right is due to IC4 and IC2. So I can get V naught. So we'll start from VCC, get the drop across RL to the left, minus, again we start from VCC, drop across RL to the right, then I'll get V naught. So this is our equation 13 over here. This is our equation 13. So V naught is VCC minus I1 plus I3 into RL, that's the drop towards the left, minus VCC minus I2 plus I4 into RL, that's a drop to the right. Now if we simplify that, open the brackets, the VCCs will cancel, and then I'll remain with the minus I1 plus R3 into RL, which is this term over here. I've just taken a shortcut and taken RL common because RL is common in both these two terms, plus this I2 plus I4. Now I'll arrange this. I'll open the inner brackets, the curved brackets. So I1 is negative, I2 is positive. So I can write I2 minus I1 into RL plus I4, because the brackets of I3 here is negative. So if you open this bracket here, it becomes I3 becomes negative. So we can write it as minus I3 into RL. And I'll put this first term of 17 in the standard form, the first current minus the second current, like here. So for me to do that, I'll have to take a minus sign outside and interchange the I2 and I1 over here. So I'll get V naught is minus into brackets I1 minus I2 RL plus I4 minus I3 into RL. That's equation 17. I think I'll have to stop here. The time is up, so I'll just make a note. So I'll stop over there for today. I'll stop over there. I know you have a class, so we'll continue the next time.